A local index is not a search server. Apache Solr and pysolr take you from a real collection and schema to a Python API returning BM25 ranked results. You'll see how to connect the pieces into a workflow that indexes documents and ranks filtered search results. I'm Professor Pi, teaching search and IR with simple Python. Search is easy to describe and harder to run well. You want the right answers fast as your document set grows. A local list or a single file index is fine for experiments, but it breaks down once you need filters, a schema, or reliable query endpoints. Solr is a proper search server. It owns the index, exposes HTTP endpoints, and gives you BM25 ranking out of the box. Python sits on top, gluing Solr to data pipelines, evaluators, and web APIs. BM25 scores documents by how often query terms appear, adjusted for document length and term rarity. In practice, that means it rewards concentrated hits and downweights very long documents. It's simple to use, works well on short and medium text, and plays nicely with filters that enforce categories or permissions. We'll build a compact pipeline, create a Solr collection, declare a minimal schema, index example documents, run an eDisMax BM25 query with a filter, and expose the same call through a tiny FastAPI endpoint. That single flow covers many FAQ and doc search needs, and it gives you a stable contract for later re-ranking or retrieval augmented generation. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we create a named collection, so Solr has an index container for documents. This snippet creates the Solr collection that the rest of the search workflow uses. Local ranking code can hide the operational boundary, but Apache Solr expects a named collection that owns the index, schema, and query endpoint. The requests.post call talks to Solr's collections API, asks for the underscore default config, and creates one shard for a compact local tutorial setup. Reply.raise for status forces any setup problems to surface right away, instead of letting indexing later fail with a confusing missing collection error. The printed output shows the HTTP status from Solr, confirming the collection exists before we touch the schema. With the collection present, we need to tell Solr how to treat the fields we will index. This example gives Solr explicit fields before any documents are indexed. Many relevance problems start as schema problems. Text fields that aren't analyzed, filter fields that aren't indexed, or fields that were never stored. The fields dict keeps the contract small. Title and body use text general for lexical matching, while kind uses string, so filters act like exact labels. Each requests.put call updates Solr's schema API for one field, which makes the change easy to inspect and retry. The output shows how many fields Solr accepted, so you can trust the schema before indexing. Now, we add concrete documents so the server has content to return and score. This code indexes the first searchable documents through pysolr. A standalone search server needs documents to cross that client boundary, so Solr add sends normal Python dicts to Apache Solr instead of keeping everything in a local list. The three docs are intentionally small, but cover the important shape, text in title and body, plus a kind label for filters. Commit true makes those documents visible to the next query step immediately, rather than waiting for a background commit. The output prints the indexed document count, confirming Solr now has content to rank. With content in place, we can run a ranked query that separates relevance from application filters. This snippet runs the first ranked retrieval call against Apache Solr. The query uses eDisMax to search title and body, while FQ restricts results to kind guide without turning that label into a storing signal. That separation matters. The main query explains relevance, filters enforce product constraints. FL includes score so you can inspect the ranking signal Solr returned, and rows limits how many candidates come back. Increasing rows gives more candidates for downstream re-ranking or RAG context. Reducing rows cuts payload and latency. The output shows the top-ranked ID and its Solr score. To make the search reusable, we wrap the same query pattern in a small HTTP endpoint. This example wraps the Solr retrieval pattern in a tiny FastAPI endpoint. Search becomes easier to reuse when callers send Q and kind and receive a stable JSON shape instead of raw Solr objects. The search function rebuilds the same eDisMax parameters. Call Solr search, rounds each score for client-facing output, and returns only the fields the API should expose. That baseline is handy for hybrid or RAG systems because re-rankers, UI code, and evaluators can all consume the same result contract. The output calls the endpoint function directly and shows how many ranked results the API would return. In a real project, this compact flow maps directly to documentation search or an FAQ assistant. Swap the 3 demo documents for your knowledge base and keep the same field contract, so downstream UI and re-rankers don't need custom adapters. When queries and filters stabilize, scale the collection with more shards and add replication. We built a small end-to-end Solr and Python search workflow that uses BM25 ranking and exposes a clear JSON API. Use this pattern when you need straightforward lexical scoring plus simple label-based filtering. One caveat: default BM25 settings are a strong starting point, but you'll usually want to tune or validate them on real queries before trusting the results in production. A practical next step is tuning BM25's K1 and B for your data and query style. Try K1 around 1.2 and B between 0 and 1 to see how length normalization and term saturation affect ranking. If you need faster retrieval on very large collections, adjust Solr's rows and shard layout, or add a lightweight re-ranker after Solr returns candidates. If practical IR helps you, subscribe and watch the IR videos.